So technically, in a control, there are two types of control system. What we have seen this physically, what we see, but technically there are two types of control system. We call it open loop control system, closed loop control system. So remember that if you are asked to explain which type of control system, whether it is open loop or closed loop, any. So open loop control system having an input, controller and processor will get an output. That's it. So here the gain that we get, that is called open loop gain. Output by input. So in the closed loop system we have the same thing, controller, process, input, output, but there is a feedback here. And we use a comparator. Comparator is this. We already have seen that. So the gain that we got here, that is called closed loop gain. The same output by input. Because we are not using a feedback here, that's why we call it open loop. We are using a feedback here, you see, it is closed. It is closed path. That's why we call it closed loop. Because it is a loop. And this loop is closed. Here we don't have any loop. It is open. That's why we call it open loop system. And because of this, we call it a closed loop system. Now, closed loop system are having other names. This name we call it feedback system as well. Feedback system. Because there is a feedback, the output is fed back. While the output is fed back, that is called a feedback system. Feedback system, closed loop system are the same. Same thing. If you are closed loop system, you can write it feedback system, it is the same. So feedback system also we can call it is a closed loop system. So all the thing, there are two types of system technically in a control system. Now there are the differences of open loop and closed loop. Open loop system is very easy to construct because we do not need any complications. Complicated devices are not needed here. We just need a controller, a process, we will get an output, that's it. But in a closed loop system, we need a comparator. Comparator compares the input and feedback, we already know. So, we also need a feedback loop. And it needs to measure many times, not once, many times. Because we are getting feedback of n times. So, this construction is complicated. So, we have a complex construction. And because of that, we have a higher cost. And here we have open loop system, we have lower cost. In open loop system we get a high gain, but in closed loop system we get a lower gain. Even if you get a lower gain, the gain is stable. In a closed loop system we get a lower gain, but stable gain. Stable gain means constant gain. Constant gain. So that's why we use a closed loop system. The open loop system does not have any constant gain. It is a high gain, but it is not constant. It is not stable. But in a closed loop gain, we get a lower gain, but it is stable, fixed or constant. We don't have any control output. This output cannot be controlled. But this output can be controlled by feedback. The output can be controlled by feedback. That's why we call it a control system. Calibration is needed in open loop system, but here it is not. So in a closed loop system, it is having a high accuracy. Closed loop system, because it is having a higher gain, a lower gain but a stable gain. We have a lower gain but a stable gain. Stable gain means accuracy is much more higher. Speed of response, the responses have more speed. The speed of the response I will talk about it later on. And the reduced effect of the disturbance with noise. It will reduce the effects of the noise. In open loop system, it cannot be controlled, so it cannot reduce the noise. Open loop system, whatever we get the output here, it is with noise. But in a feedback system, we feed it back and we reduce the noise. We can reduce the noise. So we can reduce the effects of noise. So the open loop system mostly utilizes a controller and action to obtain the desired response, whatever we want, the desired response we want. So output does not have any effect in the control action. Output here. Whatever the controller decides, whatever the controller is designed, will get an output through the system. So it cannot be controlled. And the output is just, we will measure it. We do not feed it back, we cannot compare it, we cannot do anything. We just measure it. That's it. Like there are some examples. Electric fan. The electric fan here, this is the electric fan. We increase and decrease. That's it. We increase and decrease. There is no comparison. We do not compare. We don't compare whatever the input and the reference one. So we just increase and decrease, that's it. Washing machine, toaster, these are actually the open loop system. Open loop system does not have any references, so there is no operating condition, no fixed operating condition. And the accuracy depends on the calibration. Calibration. All the time it is needed because it is an open loop system. While we get the output, all the time it needs to start from the beginning. Calibration. It will start from the beginning again. It is like this one. Turn it on. You used it and then turn it off, and again turn it on. So it needs to start from the beginning again all the time. Closed loop system does not need to start from the beginning all the time. The performance is open loop system is affected by the disturbance and variations of several external conditions, like the temperatures, the pressures. I already told you, those are the external conditions, environmental conditions. In the closed loop system, in contrast, it will control the output through the feedback system. So from the output we will get a measurement through the sensor to the comparator. Comparator will compare the input and this measurement, the output, and then it will send back to the error input to the controller, and the processor will process it. The plant will process it, and it will provide the output. So in a closed loop system, it will utilize the output again and again all the time. So when it will utilize the again and again all the time, it will reduce the error. Because what actually here, this is error signal. The controller does not get input signal directly. The controller gets here. This is the error signal, error. The controller gets the error signal, not the input signal. The error, the differences between this one and this. So when it will get the error signal all the time, because it can do the n times. It is a closed loop. It continuous. It is continuous. It will not stop. It will not stop. So it will go on all the time. So this error signal, while it gets through, it gets sent through the controller to the process, it will reduce the error. And it will reduce the error in such a way that we desire the expected response. Like the AC. The AC temperature. You fix the AC temperature 25 degree in remote. You fixed it 25 degree. But your room temperature, is 30 degree. Room temperature is 30 degree. This is what you want. Your input is 30 degree. Your remote, that is what you want. This is your reference. So here, first of all, the 30 degree, you will get 30 degree. You will get 30 degree. The error signal, it will compare with this signal 24. So then the secondly, it will get 29 degree. It will have 29 degree. Then it goes on and finally it reached to 24 degree. Finally it reached to 24 degree. Now this 24 and this 24, that steady state error will be equal to 0. The error signal will be 0. When there is no error, that means what we expected it's given, it's provided by our control system. So steady state error, they are the same. The reference 24 and we get the feedback 24. Reference and feedback 24, 24. No differences, 0. Steady state error is 0. And why it is get 0? That means we got our desired response. And this is what the control system, closed loop control system or automatic control system does. Making error signal 0. Error signal makes it 0. 0. And it is actually happens based on the reference that you provide to the control system. Now I am talking about only just one. I talked about one, that is temperature. But you can control temperature, you can control pressure, you can control humidity, any. If you want to control different variable, like here this one is T, temperature I talked about. But you can control H, you can control P, any variable. So if you want to control more than one variable, that is called multi-variable control system. That means you are controlling more than one variable in the same control system. So you need different many inputs, multi-variable inputs. That is called multi-variable control system because I have many variables at the same time in the same control system to control it. So we can use, and all the time for each one I have one feedback. For each one I have one feedback. For each one I have one feedback. For each variable I will have one feedback. And the comparator will compare it and find out the error signal here. So the error signal will be here and it continues, goes on till my steady state error is 0. Error signal is 0. It continues. Now I already told you the closed loop system, we call it a feedback control system. Why? Because the output what actually we get, that is fed back to the input again. Fed it back, while it is fed back to the input again, it will compare with the input and gets the error signal and it will produce the output and it continuously goes on and on. That's why the closed loop system, in another term we call it feedback control system. And this feedback can be either positive or negative, any value. Positive or negative, any value it can be because it is getting from the output. So it can be either positive feedback or it can be negative feedback. Alright, so these are the technical terms of the control system. We have seen two types of control system: open loop, closed loop control system. Closed loop control system, we call it feedback control system. Simply, that's what we have seen that. Now we will talk about the technical different types of control system. Technically, there are some other control systems as well. So first of all, we will talk about two different type systems. One is called linear and non-linear control system. Now, the linear and non-linear. Linear, what does it mean? This word, linear. This is actually, we call it this. This is a linear line. It is getting from here. Linear line. So this line we call it y equal mx. And this one is also linear line. This one we call it y and x plus c. This is c. You know that it is straight line, simple straight line. Linear means straight line. This is the straight line equation. Now, a control system, a linear control system, where we call where the output is linearly changing for its input. The output is changing linearly. Here, this output is changing linearly, increasing, decreasing. Here it is increasing linearly. So there are two different types of straight lines are given. This is straight line. Look, this one we can write it y mx plus c. This is m, x ut, c 1. This is c. This is c equal to 1. And because of the negative sign, it is this. This is minus mx. Negative sign, minus mx. This is plus mx. Minus mx is this. So this is c. And here, this one we can write it y mx plus c, m 3, x u, c 5. So the output is changing linearly for its input with its input to a control system that is called a linear control system. So the input-output relation is linear. That's why we call it a linear control system. Now, if it is not linear, the input-output relation. What is the input-output relation? This is input. Here I have the input characteristics. In this, I have the output characteristics. So the input-output characteristics. Look at this. From 0 to here, it is linear. But later on, here, it is not linear. We call it non-linear. This portion, we don't have a linear system because the input-output relationship is not linear here. So, but here we have the linear portion. You have the linear. Now, how we can call this system? Because we can see that we have a linear system here. Here we don't have a linear relation here. It is non-linear. Here we have linear. So how we can call this system? How we can differentiate this system? Which system we call this? Now here there is the explanation. linear system does not exist in practice. That means this system, the input-output relation, will always have a linear system. Practically, it's not possible. We don't have linear system in practically. So that's not possible. Now, so how? But we need to make sure that the system is linear. We always need to have a linear system because there is a term LTI. This term we call it linear time invariant system. And this system we call it a stable system. We always want a stable system. So if you want a stable system, we must need to design an LTI system. LTI, linear time invariant system. Linear time invariant, that means first term is linear. It has to be linear. Second term is time invariant. Time invariant, I will talk about it later on. So that system we call it stable system. So here we need to design a system that is linear, but we can see that linear system does not exist in practice. So what do we do? We fix the range of the system. We fix the input. We fix the range of the input. Suppose here we fix the range of this from 0 to 0.025, like that. Fix the range of the input. The input range will be fixed. And in that range, the system is behaving linear relationship. Here, the system is showing linear relationship. The input output having a linear relation. Now this system we will call it a linear system. So this system we will call it a linear system. Because for this range, the system is exhibiting or it is showing the linear relationship. So this system we will call it a linear system. Because practically it is not exist. So we need to fix the input. We need to fix the range of the input. And in that range, if the system is behaving linear relationships or it is providing a linear relationship, then we call it a linear system. That is how we design a linear system. We fix the range and then we measure the linear relationship, and if it is linear, then we call it a linear system. So that's how we measure the linear system, or we measure the input-output linear relationship of a system. So if it shows the linear relationship, then the system will call it a linear system. Second one, time invariant and invariant system. So second question here, I told you that we need to talk about the time invariant and invariant system. Time invariant, that means the system does not depend on time. Time variant, the system depends on time. So time invariant means does not depends upon time. Like, look at this. Here I have x. X is a function of t. X is a function of t. That's it. But it is not essentially depends on t. It is a function of t. So there is no t here. But in this, I have a t. T. That means this equation depends on t. This equation does not depend on t. If it depends on t, this system we call it time variant system. This one is time invariant system. Because the system, this equation does not depend on t. There is no t here. There is a t, but it is a function of t, function of x. So it is not essentially depends on t. It is time invariant. That means no time dependence. No time dependence. But here this equation depends on t because this is not a function. This directly depends on this value t. So this system we call it time variant system. So in a stable system we need this time invariant. That means this. Together linear and time invariant. LTA we call it an LTA system, and that system we call it a stable system. Remember that. Now the next one is continuous system and discrete system. For the data that we use, the input that we use here. The input that we provide here, this input can be two types. Whether it is continuous or it can be discrete. So we need to talk about this, the inputs, which type of input it will be. So based on that we have two type of system. One is continuous system and discrete data system. The continuous system, this is a continuous system. This one, that system we call it analog system. All the analog system are continuous system. This is an analog system. So the continuous data control system, all the system variables are function of a continuous time t. This is a continuous time. This is t. This is t. So all the variables are functions of t. So this is a continuous system. It is continuous all the time. You cannot separate any data. You cannot separate it. But here, if you see in a discrete system, it involves one or more variable in discrete time interval. This time you cannot separate it. But now here, this one you can separate this. You can separate each time. This is also t. We define it in n because this is done by a process called sampling process. This is done by sampling process. So it will be a t will be converted to n. So now here, if you have, we have specific point. Here we don't have any specific point. Here we have a specific point, and each point I have value. Each point I have specific value. That's why it is called discrete. Discrete means separate. Not join. Separate. You can separate each time. You can separate each time. And each time I have a fixed value. Each time I have a fixed value. That's why we call it a discrete system. This discrete system is done by a process. That process we call it sampling process. This process we call it assembling process. We will talk about the assembling process later on, not now. We had some explanations based on that later on. Now, also there are two types of system. We call it deterministic and stochastic system. Deterministic system means repeatable. Like here. Here, if I talk about this, what is this? Sine wave. Now, look, this one is repeating here. This one is repeating. So again, if I talk about this, if I just divide it, this one is repeating here, this one is repeating here. This is called deterministic. Suppose here another one, I have this. So separate. Now this one is repeated here, this one is repeated here. Repeating. So while you have a system that is repeatable, that is called deterministic. Repeatable system, repeated all the time. If it is not, then we call it stochastic system. A stochastic system mostly we call it a random system. Random. Stochastic means random system. Look at this. Suppose if I draw a wave like this, it is also a system, but it is not repeatable. It is not repeating. It is random. The values are random all the time. Random. That is called stochastic system. Now, in our practical world, we don't have this. We have this. In our practical world, we have stochastic system. We have random system. We don't have deterministic system. You always learn this deterministic system because it is easy to explain. It is easy to explain mathematically, to analyze it mathematically. That's why we learn this. But in practical world, we don't have this. We have this. Continuous system. Dynamic system is always stochastic system. Dynamic system. Dynamic. This system, the practical system, it is a dynamic system. It is a changeable system, random system. It is not a deterministic system. Deterministic system we only use it while we do the mathematical analysis because it is easy to solve. But practical system is this. Now what we have seen so far, all these classifications are given here. The classifications. There are, first we learn two. The control system, natural, man-made. Natural, man-made. So man-made system there are two, manual and automatic. We have seen manual and automatic. Automatic system, two types, open loop, closed loop. Open loop and closed loop. Open loop system, there are two types, linear, non-linear. Closed loop system, two types, linear, non-linear. And each linear, non-linear, we have time variant, time invariant. Linear system, time variant and invariant. So here, what we actually want, we want an automatic system that is having a closed loop that has to be a linear and that has to be a time invariant. So first it has to be an automatic system, closed loop system, linear system and time invariant system. So this is what actually we expect while we design a system. That is called an automatic control system. has to be a linear system and time invariant system. Remember this. So this is what actually we have seen so far, we learned so far. An automatic system it will be a closed loop system. It will be a linear system and it will be a time invariant system. Shortly we call it an LTI system. Alright, there are some requirements of the ideal control system like what are the requirements? Accuracy. An automatic control system has to be highly accurate. Highly accurate means it has to be a constant gain. The gain. Stable system. Highly accurate means having a constant gain. Even it is lower gain, but it has to be a constant gain. Open loop system does not provide that. Sensitivity. Sensitivity. It has to be highly sensitive to its input. The input that we provide will be provided. So the input has to be, the system has to be highly sensitive to its input and highly insensitive to some external disturbance or internal disturbance. So sensitivity is very important. So we need to measure the sensitivity all the time while we design a system. Third, external disturbance and noise. We always need to reduce this external noise or disturbance. So disturbance or noise always happens in a digital circuit all the time. It is quite common because we are using different devices. So because of those devices and because of the external conditions and because of that the noise happens, noise occurs, and that noise has to be reduced. How do we reduce the noise? By using a closed loop system and by finding the error signal, steady state error, SSE. Always find the SSE, and if you find the SSE, you can find out the noise. You can reduce the noise. SSE is 0, that means no noise, no disturbance. Stability, it has to be a highly stable system. Now, the highly stable system means what? Highly stable system means it must need to produce or it must need to provide a BO, stability, BO, bounded output for bounded input, bounded input, bounded output, bounded input, bounded output. So the bounded output, we shortly call it BO stability. What is that? BO stability. BO stability, this the input has to be greater than 0, less than infinity. This is input. This Bx is input. And this one is output. That means BO stability will produce finite output for the finite input. That is what we call BO stability. For the finite range of input, it has to be produced finite output. Finite, not in the infinity, less than infinity, less than infinity. That means finite input for the finite output. That is actually produced by the BO stability. So that stability, then we call it a stable system. Bandwidth. The bandwidth has to be needs to measure because we already know that linear system does not exist in practice. So it has to be a certain range, and that range we can measure it in frequency. That is the frequency range. So there has to be a certain frequency range, and that is called the bandwidth for the stable system. Speed, a system, good system having a high speed, high speed. So if it will not provide a desired response in a very short period of time, then it will not be a good system. Because like if I am just pressing this, it has to be gone to the upward and downward while I am pressing, not after 2 minutes, after 1 minute. Same time, real time. So that system we call it a real time system. Real time system needs to have a good speed, high speed. Oscillations mostly happens for the damping. Damping we will talk about it in a first order and second order system. In the second order system there is an oscillation, damping. So in the damping system we have different types of oscillations. So the oscillations needs to follow the input. The output oscillation needs to follow the input. No overshoot. Overshoot means this. Overshoot means this. So this is called overshoot. You see, there is high overshoot, there is low overshoot. So we expect this. We always expect this one for the damping, for a good system. Here we have some examples. Already I have already told you this water level fluid regulator, that is the automatic water level regulator. This is done by this valve. So when it goes up, it touches here and the water this is the water flow. This is the water flow. The water flow. And while it touches, stop. And it is controlled by this float bar. So while there is no water, it is open. While it is having water, so it goes up and it will touch the valve and there will be no water flow. So this is the automatic water level controller. I already explained it to you. This is the manual water level controller. Manual because this guy is looking to this water level and he is changing this valve manually by his hand. So that is the manual control system. Third one, the modern control system. In the examples, this is airplane. In the airplane, there is a gear. This gear. This is called the gear. So in this gear, if you turn it right, left, or right, or forward, or backward, based on that, the airplane will move in right or left, or up or down, or forward. So depends on this gear. So this is a very important. This is the control system. This is the control system. It controls the whole airplane movement only. The movement, right or left, or up or down or forward. That's all about today's lecture. We will talk about the mathematical modeling in the next class.